happen after 24 hours of casting. Holt and Livio in 2004 mentioned that the early age cracks can be opened at later ages and lead to problems. Curing of content. Let us just quickly go through the conventional methods of curing. We are using four different types of curing. Three basically. One is using water, second is using membranes, third is application of heat, and four is miscellaneous. Water curing is the most commonly used type of curing. It is very cheap and it is easy to do. So we all resort to water curing primarily. Here, what we are trying to do is keep the water, use the water to keep the concrete moist and prevent the water from the concrete to escape. So it promotes hydration and absorb heat of hydration and eliminates shrinkage. Different commonly used methods are immersion, ponding, spraying or fogging, and wet covering. Immersion can be used for laboratory work or factories, precast members and so on. Ponding can be used for a bigger surface like slabs. Spraying and fogging can be used for also wet covering can be used for columns and structures like that, where the other easy methods are not feasible. Then coming to membrane curing. In membrane curing, what we are actually doing is we are creating a seal and we are preventing the water already there in the concrete. We have calculated the quantity of moisture that is required in the concrete for hydration, and membrane curing is very simply we have enough water there and we are not allowing it to escape. Usually, before start applying the membrane curing, it will be water cured for a very small time, and then we will be using a membrane to protect the water from evaporating. But the process is a bit expensive due to the materials that are required, and also required very skilled labor and good supervision. Even a small hole or a puncture in the membrane will cause to have different outcomes than that we are expecting. Usually commonly used materials are bitumen, rubber compounds, polyester, polythene filling, waterproof paper, etc. Actually, the membrane curing is very similar to internal curing in the view that both of them are using the water that is already there in the concrete, which can be treated as a process of self-curing itself, because the water, we are not adding additional water there. Then application of heat. The rate of hydration depends on temperature of concrete. So we have to maintain the temperature and adequate moisture in the concrete to accelerate the rate of hydration. This can be achieved by using heated steam to concrete. Steam curing, as you will be having accelerated curing tanks in your laboratories, and ordinary pressure. Steam can be used to cure maybe in say 3 days, and steam curing at high pressure, that is what we call as autoclaving. 28-day strength can be achieved in 1 day. This you might be using in your laboratories, especially if you are doing mixed designs. We may need to have accelerated curing tanks to get the outputs at an earlier date to finalize the final mix design. Next is curing by infrared radiation and electrical curing. Both of these are not that much required in our climate, which is a tropical climate. But when the temperature is low, you have to keep the concrete warm enough to accelerate the hydration. Again, whatever be the method of curing that we are using, it is very difficult, as I have mentioned earlier. If the water is lost from the internal surface, internal body of the concrete, It is very difficult to transport water back to the center of thick elements. Even though you are going for immersion curing, it is very difficult. Because of the concrete is having less permeability, the water may not, and the cracks and pores are very small, and the capillarity will not allow you to transport back the water into the center of the concrete. So internal water reservoirs are very much essential for proper hydration of the cement in concrete, which which is very crucial in determining the gel pore structure. Internally cured concrete is very much lesser prone for self-desiccation, and a very important report is published by RILAM, that is RILAM Technical Committee on 196, that was published in 2007 and is available in the RILAM website for downloading. This report have the state of art of curing, conventional methods of curing. Then we come to internal curing. The, the first paper, the oldest paper that I have found about this is in 1997 by Reinhardt. So he suggested that lightweight aggregate which can absorb water can be used to create internal water reservoirs. Lightweight aggregates were used earlier for reducing the weight of the structure. But this perspective was suggested by Weber and Reinhardt in 1997. Use of chemical admixtures in concrete which can retain the water by means of chemical bonding can also be uh, used for internal curing, that is self-curing. When I say internal curing, it means it is synonymous to self-curing. So when the we are using chemicals to bond water, which is having lesser chemical potential than the uh, hydration of cement and water. So when the water that is free is used up, the chemical bond between the compounds are broken down, and the water will get attached to the cement, and hydration takes place. This is what we use to do in chemical bonding. The most commonly used chemicals are super absorbent polymers, which can absorb very large quantities of water. We are using it in different areas. The silica gel that we have, along with any electronic products to prevent it from moisture. You might have seen it in packing. The diapers, the sanitary napkins, everywhere we are using it, but the same thing can be used in concrete to absorb water and retain it internally to create internal water reservoirs. Next is internal curing using lightweight aggregate. So pre-soaked porous lightweight aggregate can create and hold water reservoirs inside the mass of concrete, which can be used for hydrating cement once the free water is used up. The process is very simple. The theory is simple. The calcium silicate hydrate gel is having lower pore size than that of the porous aggregate. So due to capillarity, the water that is there in the porous aggregate, pores of the porous aggregate to be exact, will be getting absorbed into the capillarity pores of calcium silicate hydrate gel, and the water will be available for hydration. So the concept is smaller pores draws water from bigger pores. That is a concept. It's a very robust technology because we can have the compaction and everything as usual. But the problem is when you are using porous aggregate, it may be affecting with affecting the strength. It is where the super absorbent polymers is very much useful because most of the super absorbent polymers are liquids which can easily disperse in water. We will come to that later. Anyway, RILEM Technical Committee 225 on SAP, super absorbent polymers, prepared a state of art report, and this also is available for download in the RILEM website. So, what is super absorbent polymer? In photograph A, you can see a small crystal out there in the left and a bigger one on the right. The one which is on the left is the photograph of a sap before absorption of water, and the one on the right is after absorption of water. So you can see how much bigger, how much quantity of water it can absorb compared to its actual size. So schematic representation is on the right hand side as figure B. This sap is widely used in hygiene industry, landscaping, firefighting, food packing, and everywhere. The sap absorbs water due to osmotic pressure, and it absorbs water till the it reaches at equilibrium in osmotic pressure between external and internal forces. So once it is there, it will be stable till the external osmotic pressure drops. So that is how it can retain water in the mass of concrete. Sorry. If sap is distributed uniformly throughout the body of concrete, this will result in an internal water reservoir is distributed throughout the volume of concrete. Very, very simple. If you can distribute sap uniformly throughout the body, then the reservoirs also will be distributed towards the volume of the concrete. Here is a representation of sap. You can see the first figure, which is a representation of sap on a bigger, in smaller scale, and the second figure is actually the hydrated sap particle. And once time passes out, what you can see in figure 3 is the result. The water is again given back to the concrete. Whatever it has taken from the concrete is given back to the concrete, and it shrinks down. The ionic concentration of the pore solution in cement paste is dependent on the hydration rather than the degree of hydration. That is very important. So, the ionic concentration will be maximum at the onset of mixing, that is at the beginning, and remains without much change till setting happens. But after the concrete attains its setting and precipitation happens in the course of time, the ionic concentration drops. This depends largely on the alkali content of the cement. So, the ionic concentration of, or rather the dosage of sap has to be decided considering the alkali content of the cement also. Presence of other ingredients like other admixtures or alkalis in aggregate may affect the efficiency of the sap. So this should be carefully worked out based on the available data, and trials has to be done before actually using it, especially when you are using supplementary cementitious material. As I have mentioned earlier, when the hydration proceeds, self-desiccation occurs, and a gradient is generated in concrete between pore fluid and sap. This can also be due to the loss of water, um, both external and internal. Okay, so changing osmotic pressure also contribute to this. then the condition become favorable for sap to release the water back to the solution. So desorption happens, which is actually the inverse process of absorption. It will release water and the sap gets shrinked and water will be made available to the concrete for hydration. Lura and al. In 2012 described this as a competition between sap and pore fluid for water. When the pore fluid is having sufficient water, that is more water, sap absorbs it, and when the pore fluid having less water, sap releases it. So this is the basic thing. And this kinetics is very much is having a large effect on the hydration microstructure and properties of concrete. This figure is taken from Mooring 2009. This is a microscopic image of a sap particle in cement with water cement ratio 0.5. On the left, we can see figure A, sap in fresh cement and sap after 24 hours. We can see a corona around the sap particle because this is due to increase in water cement ratio locally, which is actually released from the sap particle. Here I have calculated the diameter and zone of influence. It says like 168 micrometer to 280 micrometer, and which means water has been transported to at least 50 micrometer to 60 micrometer. Toledo in 2012 described this process as sap as equivalent to removing some quantity of water from the mix, and hence sap is to be used and extra water is not added to compensate the tendency of infection. It may affect the workability of the concrete. So this is a different perspective that when sap is used, it absorbs water, and then extra water has to be provided to the concrete to compensate for the workability. We'll come to that later. According to E and all, in 2012, sap acts as a soft aggregate when it is filled with water and acts as a fluid stage when it is dried. And he says it is difficult to obtain uniform distribution of sap in concrete mass, but this is not true. Earlier, researchers thought that it is not possible to obtain uniform distribution, but later studies shows that it can be properly distributed throughout the system by using proper methods of adding sap particles. The effective water cement ratio is altered at an early stage of hydration due to absorption of mixing water by sap, and additional pores may be induced at the interface of sap and cement concrete phase. Many experiments has been conducted by various researchers, and it was confirmed that concrete microstructure can be altered by the addition of sap. And some of them were positive, some of them were negative. And as time passes, we learned how to use these sap particles properly to obtain better results. So the procedure by which it is added to the concrete and the quantity of dosage, the dosage of sap is very much important. Plastic shrinkage and autonomous shrinkage, drying shrinkage and carbonation shrinkage that we have discussed earlier are different in their nature, and the effect of sap on all these are different. These shrinkages were defined by Le Chatelier in 1900. We are still using his terminology. The absolute volume of concrete is the total volume of all ingredients, and the apparent volume is the actual volume occupied by the concrete, which includes gaseous phase also. Change of apparent Absolute volume is chemical shrinkage, and change of apparent volume is known as autonomous shrinkage. Let us revisit the plastic shrinkage. Plastic shrinkage is rapid loss of moisture from the surface immediately after casting, but before hardening. Then we can view this concrete as a drying suspension of very densely packed solid particles in a liquid medium. So the evaporation from surface is the main reason for this type of shrinkage. When the surface, after laying and placing the concrete and compacting it, finishing it, we observe a very slight thin film of water on the surface. And if this water is completely lost, then the pores will get open up and the water from the pores will evaporate. Then this pores cause capillary rise of water from internal, and it causes further loss of moisture. And if there is a restraint for movement, partial shrinkage becomes visible. This is capillary pressure against time. So initial stage at here at B, you can see the bleeding. Then capillary pressure is building up here. After bleeding, once the surface moisture is lost, we are having a surface film here. Once it is lost, capillary pressure build up and it draws water from the inside, and the capillary pressure increases and draws more and more water and break through. And once it break the film, the water from internal will start coming out and getting lost to the atmosphere. And this is what I have mentioned earlier. The plastic shrinkage can be controlled by using SAP into the system, superabsorbent polymers into the system. As I have mentioned earlier, chemical shrinkage is a change in absolute volume of concrete. But this is not that much considered by the researchers and engineers because once the concrete takes its form, the chemical shrinkage is cannot be measured. But it is very important in determining the macroscopic autogenous shrinkage of concrete. Researches were done by many people in reducing the shrinkage. So studies were done for studying the effect of SAP and silica fuel. So the chemical shrinkage is observed to be more when mixes containing SAP is tested. So this is the due to the inability of water to penetrate through denser matrix with lower size that is created using SAP. Autogenous shrinkage is change of apparent volume, as I mentioned earlier. The change of volume without significant change in its mass and temperature. This is actually happening due to the macroscopic pores throughout the concrete mass on hydration of cement because of the large magnitude of chemical shrinkage. Internal shrinkage happening to the concrete volume cannot be measured directly since it will not make any change in the apparent volume of concrete. Since the magnitude of autogenous shrinkage is very much lesser than that of drying shrinkage, This was ignored till we started using high performance concrete. When high performance concrete become very popular, uh, this high performance concrete is very prone for autogenous shrinkage, and people started uh, focusing on autogenous shrinkage of high performance concrete. This is particularly true when there is a high performance concrete with a lower water cement ratio. The shortage of free water that is available for hydration of cement and internal relatable humidity causes autogenous shrinkage in high performance concrete. This also creates tension in pore water uh, because of the reduction in ministry of pore water, and this all causes autogenous shrinkage. The compressive stress developed in concrete causes a reduction of volume of concrete because it shrinks. If SAP is used, internal water reservoirs can be distributed throughout the volume of the concrete, and water can be made available internally and reduce the autonomous shrinkage. Some researchers even found out that introduction of SAP into the system can actually reduce autonomous shrinkage and even cause expansion of concrete. This is a schematic representation of shrinkage. The chemical shrinkage, subsidence, bleeding, autonomous shrinkage, chemical shrinkage, everything is mentioned there, self-explanatory. Then Jensen and Hansen in 2002 studied the effect of SAP on drying shrinkage in cement concrete. The drying shrinkage is observed to decrease with increase in SAP content. Mooning again observed the loss of mass due to drying is lesser for mixes with lower water cement ratio. McCathrin and all in 2009 observed that the decrease in quantity of curing water increased the drying shrinkage. He attributed this internally cured concrete to the availability of large quantity of water in a concrete internally cured using SAP. Uh, Please excuse me for a minute. I'll be back in a minute. I'm sorry. I was having a meeting at 11 o'clock. I had just made that arrangement for another half an hour. So that's why I went. Okay, we'll continue. Again, studies are done on self-cured concrete, on high performance and ordinary cementitious materials and different type of materials, the procedures, the permeability, isothermal dyeing, weight loss, relative humidity, everything. So, prevention of autogenous shrinkage cracking of high performance concrete in which sand is replaced with pre-soaked lightweight, and here as I have mentioned earlier, people have tried different methods. There is an important study by Kusen and all in 2010. They evaluated the benefit of high performance internally cured self-cured concrete in brick decks in terms of their service life and associated life cycle cost. This study was an extensive one which was funded by the US government, and they have found out that the predicted that the service life of bridge decks are significantly uh, increased when internal curing is used, which means when the life increases, it means the life cycle cost reduces considerably, more than half of that is required for ordinary concrete. This was basically attributed to the less maintenance and longer service life due to low permeability of internally cured HPC. Coming to the patent in this regard, Chow in 2011 was awarded a US patent for demonstrating the importance of maintaining sufficient moisture curing cream of concrete. He demonstrated different things. One is the micro cracks, development of micro cracks due to shrinkage caused by alternate wetting and drying in case of conventional curing. Then about self-curing concrete, he defined it as in two dimensions. One is which does not have requirement of labor for curing of concrete. The second definition is more important. He defined it as in the patent concrete that does not any further external curing after placing of concrete can be deemed to be self-curing concrete. This is the definition that we commonly use for self-curing concrete. That is, it does not require any further external curing after placing of concrete. He also proposed to add different self-curing agent, that is, can be any polyvalent alcohol, polypropylene, like different compounds are there, and restricted the dosage in the range of 0.5 to 5% by weight of cement in concrete. Then mechanical properties. Many scientists, as mentioned here, have observed that the strength is getting reduced on application of SAP. This is very important to note that earlier researchers obtained reduction of strength or even similar strength that of concrete, conventionally cured concrete. But later on, as time passed by, researchers became aware of what their problem was. It was the problem with the dosage and the method of application. And then reports came, or researchers came forward with positive results regarding SAP. So we have to learn from the failures and to move towards using it in proper way. That is why I have included these two different sort of researchers into this particular presentation. Because when you observe the mechanical properties of concrete over a period of time, earlier researchers says that the concrete are having inferior properties or no improvement are there. But later on, researchers are reporting that significant improvement can be made in the strength and durability of concrete in the case of concrete cured using superabsorbent polymers. And I'll quickly go through my study, in which I have used polyethylene glycol for curing concrete. Polyethylene glycol is a polymer of ethylene oxide with a molecular mass below 20,000 gram per mole, which is widely used in medical, biological, chemical, and industrial use. Some of the molecular weights, some of the PEGs are having very high cost, whereas some others having very low cost. So naturally, I have tried to, because the economics has to be considered. So I have tried to use PEGs of lower expenses, and that is mostly available. This can be either liquids or pellets. But the physical properties depend on their length. Their molecular weights and chemical properties are found not to be much associated with their molecular weights. So, irrespective of the molecular weights, we can uh, we can actually use them for curing concrete. And PEG is soluble in water. It gets coupled to hydrophobic molecules forming non-ionic surface tension, which is actually what we are using to disperse it uniformly throughout the water. Since it is soluble in water, we can mix it in water, the mixing water for concrete, and it can be uniformly distributed by using conventional mixing procedures. That is the advantage. I have used different types of PEGs, different molecular weights of PEGs. On the left two are liquids and the white plastic packets, those are pellets, which has to be mixed in water to get into the liquid form. There was a study on M30 concrete. The the cement, the fine aggregate, and the mixed design. I'm skipping through this because what is more important is the outcome. And I've done different testing, electrical acidity, sulfate resistance, water absorption, etc. So here, just understand that I have used three molecular weights of PG, 600, 4000, and 6000. And so in the range 0, 0.5, 1, and 1.5 percentage by weight of cement. Okay, so this is the nomenclature. You can see that this D is 0 PEG, that means conventionally cured specimen. So you can see that compared to D, almost all PEG cured specimen is having better strength, and some of them are having lower strength because the dosage is not in the proper way. Similar is for splitting tensile, modulus elasticity, water absorption, electrical resistivity also similar nature, sulfate resistance also similar nature. Considerably reduce the increase the sulfate resistance. Weight loss is very low when compared to the compressive strength. Have used the rebound hammer to assess whether the rebound hammer is proper, can be used for testing the predicting the strength of concrete. So ultrasonic pulse velocity test is also used to assess the quality of concrete. This I have repeated with the M30, M40, M50, M60.
Sir, excuse me, sir.
Yes.
Sir, can I have one doubt, clarification from you, sir?
Just a minute. I will just complete this in a 5 minutes. Then
Okay,
we can.
okay. No problem. Okay.
Anyway, I'm going to share this slide with you for your reference, and I will quickly go to there is improvement when compared to the tensile strength, compressive strength, and modulus elasticity of concrete in comparison with the immersion cured specimen. And the observation is that use of PEG is more effective in lower grades of concrete. This is my personal observation. Dose of PEG is required is also found to be increasing with the increasing grade of concrete. The dose of PEG is higher for PEGs of lower molecular weight than PEGs of higher molecular weight. Okay, then we have seen we can see the magnified images of pore structure. You can see that when PEG is employed, it results in better pore structure than the conventional water cured specimens. Again, this is another zoom. The zoom was 3000 and 5000 respectively, 5000 times respectively. So PEGs can be found to be effective in attaining the required properties of concrete without any external curing. Strength and durability properties exhibited by specimens can be Better can be using PEGs. Microsystem is also better. As I have discussed earlier, the PEGs is more effective in lower rates. Then dosage of PEG is also found to be increasing with increasing grade of concrete. Ultrasonic pulse velocity tests also reveal the superior structure of PEG cured concrete. Rebound hammer values is observed to be slightly below the actual compressive strength. So the rebound hammer test is going to give you a conservative value. This is actually because it is cured internally also. The rebound hammer is basically seeing the surface hardness, using the surface hardness for predicting the concrete strength. So we can, in short, what we can do is we can use PEGs to have better concrete with better strength and durability. Uh, so I have just made it rush through the my results of my experiment. It's because I have to attend another meeting. So the meeting has already started. So I have to naturally rush through. So anyway, it is open for discussion. I appreciate and be is thankful to you for your patient listening. So if you have any questions, please.
Sir, excuse me, sir.
Yes.
My name is Vishnuvardhan.
Okay.
Sir, actually, your presentation is so good and the content is also so useful for the students and research scholars.
Thank you.
And actually, my question is: has there been any studies upon the optimum dosage of study, sir?
Yes. Very good question. See, this is what I have tried to emphasize through my entire presentation. That is why I have added negative results as well. See, there are different parameters like alkali content of cement, osmotic pressure, the pore fluid concentration. There are different parameters that are going to affect the ability of SAP to uh, cure the concrete properly. So definitely, as far as it is concerned, now maybe we will get a clearer picture later. But as far as the available researchers and my own experience, it has to be calculated. It has to be done on trial and error basis. And but I can say it is zero point 0.5 to 1.5 percentage by weight of cement. You may find depending on your aggregates. Even if the aggregate is having alkali content, definitely it is going to interfere with your dosage of SAP. Am I clear? I think I have made it clear. Any other questions?
Uh, uh, Good morning, sir. Good morning. Yeah, good morning. Is my voice audible to you?
Yeah, yeah, sure, please.
My specific question is, we have such tall structures like Burj Khalifa and all, and
Mhm.
such tall structures are going to come up in the coming years.
Okay.
Now, how do you see the scope of, self-curing concrete in such applications?
Yes, that's a good question. See, self-curing concrete is not that much widely used in the field because of it has to be optimized before it is widely used in the field, and it is used in locations where other methods of curing are not feasible. Like in the case of high-rise structures, definitely it is going to be self-curing concrete sooner or later. I think some portions of Burj Khalifa itself is cured using self-cured concrete, but I am not sure because it is not authentic literature. It was actually from newspaper articles, but I am not sure. Definitely, when as time passes by, this become a viable solution for curing. but things has to be evolved, and methods and like now we have to calculate everything, and maybe we have to do trials and execute in the field. It will become more and more clear as time passes by, and more researchers will be coming up in this area. And there is actually a lot of research space, research gap existing in the system. So definitely, as and when time passes by, it is definitely going to be the time for self-curing concrete.
Yeah. Thank you. Thank you.
Thank you. Thank you for the question. That question was very good question. Anything else? And one word to the